Okay, everyone, good morning. We're now starting with this session of Onward papers. My name is Riemen van Rozen. I will be your session chair. The common thread of this session is novel solutions for existing code and data, clone detection, software rejuvenation, and refactoring. We have 3 talks of 30 minutes each. At the end of each talk is some time for questions. We'll be using this microphone to do those questions so that online participants can also hear us. I would like to ask everyone to mute their mobile phones, which is apparently still necessary to ask. And let's see. We begin with the first talk by Samyak Jhaveri on a quantum solution to duplicate code.
Yeah. Hi, everyone. Thank you so much for coming to my talk, first conference. So I'm here to talk to you about our most recent research paper, Cloning and Beyond, a quantum solution to duplicate code. Many of you know about code clone detection and duplicate codes, but here we are trying to present a quantum twist to not just code clone detection, but expressing software engineering problems in general as optimization problems to be solved on quantum computers. So let's start. Why is it not? Yeah, so I'm going to start by first introducing what we are trying to do and the significance of our research, and then dive a little bit into how to think for quantum annealing, which is essential to completely understand the concept behind quantum annealing and quantum computers to solve problems on them. And then I'm going to talk about using mathematical frameworks to express software code clone detection as an optimization problem, and then tell you a little bit about how we experimented with the algorithm that we developed and the results and analysis and what it means to the research communities, what we're trying to present. So one of my favorite scientists growing up, Richard Feynman, said this in 1981. It's been 40 years since he said this, and there has been lots of research in physics, mathematics, and computer science about quantum computers, but only now, since the last 7 or 8 years, we've seen commercial applications of quantum computers become a reality. The motivation behind our research is to bridge the gap between what we already know and what we're familiar with in software engineering and what comes next in quantum computing. We have tried to use code clone detection as an example of how software engineering problems can be expressed as optimization problems and can be solved on quantum annealers. So let's dive headfirst into quantum. You may have heard about universal gate-based quantum computers from companies that they are beating their own records in the number of qubits that they introduce into their systems, or beating quantum supremacy every few years, every now and then. Those quantum computers are gate-based, which means that they use quantum gates to manipulate the state of quantum bits, or qubits, just like a classical computer, but the difference is that qubits are capable of being in a state of superposition, which means that they can be 0, they can be 1, and they can be 0 and 1 at the same time. And other quantum mechanical properties like entanglement or quantum tunneling. Lots of research going on in this area, but unfortunately, it's still very new, which means that there are still lots of errors or noise in the quantum bits, which makes them infeasible for large-scale applications. Most of those errors comes from external noise or the very fact that quantum superposition is a very delicate state for qubits to be in. The other kind of quantum computers that are relatively less known are adiabatic quantum computers. You may have heard about simulated annealing. Adiabatic quantum annealers or quantum computers are essentially a hardware implementation of simulated annealing, where they try to minimize the energy of a system by solving certain objective functions. The way that it works is you can express a problem in a certain mathematical framework, which I will elaborate upon later in this talk, and it is specified in detail in the paper as well. And expressing those problems and embedding them onto qubits inside one of these adiabatic annealers. The cool part about quantum computers is that most quantum computers need to be superconducting, which means that the qubits, to be in a state of superposition and entanglement, need to be superconducting. And because we don't have room temperature superconductors, they are super cooled to really low temperatures, as low as 15 millikelvin. Yes, that's colder than outer space. So where does clone detection fit into all this? We've tried to express clone detection as an optimization problem and solved it on a quantum annealer. And the approach that we're using, the thinking paradigm, the thinking mindset that we're presenting in our paper, is applicable to other graph-based problems as well. And for those of you who do know about the types of code clones that typically exist in a software system, we know that there are 3 types of code clones that are syntactic, and the 4th one is semantic. Our research focuses on the first 3, type 1, type 2, and type 3. And type 3 code clones are computationally intensive to detect. They're very messy in some cases and difficult to detect. There have been many approaches and tools and techniques that use graph-based graphs, like program dependency graphs and ASTs, abstract syntax trees. And even then, they are really good for precision and recall, which are important metrics for code clone detection. But even then, they're very slow. And to make them practically feasible, there needs to be applied lots of aggressive heuristics, which also introduces some false positives and false negative errors. One way is to forgo graphs altogether and use tokens instead. But even then, those approaches typically suffer from false positive and false negative errors. So in our research, we show how we express code clone detection as an optimization problem. And our technique is also able to detect type 1, type 2, and type 3 clones. So what are the contributions? We start off with formulating subgraph isomorphism as a QDO. I'm going to expand upon this in the talk. And a critical component of our application is adding node type constraints, which is comparing the nodes of 2 ASTs to make sure that you're comparing the right types of nodes when you're trying to map one AST onto the other. And lastly, we are empirically evaluating our algorithm and getting a really good idea of what we can expect and what we cannot expect from quantum annealers in this present state that they're in. So, how to think for quantum annealing? It leverages the quantum adiabatic principle. The physics needs to be abstracted away for us computer science folk, but I'm going to dive a little bit into it just because to give an intuition of how these problems can be approached. So, optimization problems can be NP hard or NP intermediate, and there are not a lot of classical algorithms to solve them in a reasonable amount of time efficiently. Also, that is arguable because on a case-by-case basis, there have been classical algorithms that have been successful. But even then, generally, some optimization algorithms fall into bounded error quantum polynomial time, or BQP, which is the complexity class that captures the power of quantum computers. Theoretically, the time it takes for a quantum computer to solve a problem is independent of the scale of the problem. And that is what makes it really a fun research area, because we want to find out in what cases and how scalable these quantum algorithms can be. That is the D-Wave quantum annealer that we've used. It has more than 5,000 qubits. To put it into perspective, gate-based have at the most 500 qubits or 430 qubits, and these have 5,000 qubits. But they're very different types of qubits from gate-based. This is what it looks like inside the cryogenic chamber. and the chip at the end is the qubit chip, which has the qubits at super cool temperatures. And it uses superposition and entanglement and quantum tunneling. So essentially, when we try to express any problem as optimization, our objective is to map the two graphs of the ASTs of two given code fragments and find a way to express it as a mathematical framework, and the final resultant energy of the minimization has to be as close to as possible as zero. So the main challenge is to find an algorithm, to formulate an algorithm in such a way that it penalizes incorrect mappings. So as you can see here, we're trying to compare two different graphs. Let's call the one on the left as G1 and the one on the right as G2. And the objective of mapping one graph onto the other is to minimize the energy of that mapping, which means the lower the energy, the more similar the two graphs are. And the challenge is to specify the penalties in such a way that every time there is an incorrect mapping, the energy of the system goes up. So when you're trying to minimize the energy of the system, energy of a system, you want to assign the minimal energy to the situation in which both the graphs are isomorphic, which means that the lower the energy, the more similar the graphs are. The higher the energy, the more dissimilar the graphs are. So the QUBO model that we designed is designed to assign a fixed penalty value to the overall energy of the system every time an incorrect node-to-node mapping or an edge-to-edge mapping is made. So the resultant energy, if the resultant energy is zero or close to zero, it means that they're isomorphic. If it's higher, much higher than zero, it means that they're not isomorphic. So I've been talking about graph isomorphism, but essentially, when you try to compare the ASTs, there's a chance that the two graphs could be of different sizes. So we want to formulate it as a subgraph isomorphism instead of just graph isomorphism. So the three main contributions of our algorithm are, number one, the node mapping penalty, where every node of G2 is mapped to only one node of G1. This ensures injectivity instead of bijectivity by penalizing only the mappings from G2 to G1 and not the other way around. Secondly, there is the edge mapping penalty that ensures that the edge present between two nodes in G1 is always mapped to an edge present between two nodes in G2. Otherwise, the formulation is penalized and the energy increases. And lastly, we have introduced the node type comparisons. The nodes of these two graphs may have different node types. And if you're trying to map one graph onto the other, there is a chance that they can be topologically similar, which means that they are isomorphic topologically. But even then, because the node types are different, they are not exactly code clones. So the second critical step is to compare the node types when we're trying to map one graph onto the other. And this is what makes it possible to detect type 3 clones that are functionally similar but have different types of elements performing the same functionality, like a for loop and a while loop. So how did we design the experiment? We wrote 6 sample programs, and at the codes of these, and we created code clones of these 6 sample programs for a total of 25 code fragments as per the transformations needed for type 2 and type 3 clones. So essentially, we have 25 code fragments. We compared each code fragment with all the other code fragments for a total of 325 pairwise comparisons. And because we developed 2 DQM formulations, QDO formulations, one with node type constraints and the other without node type constraints. And we performed all those experiments 10 times to make sure that we're getting good results. So a total of 6,500 times we measured our algorithm. So this is a little bit information about the experiment hardware itself, the D-Wave Advantage Quantum Annealer. We used the Advantage Quantum Annealer because it had hybrid computational capabilities, which means that it uses QPUs, quantum processing units, CPUs, and GPUs all in tandem to solve these problems, which allows us to solve bigger problems because then you can break the problem into smaller chunks and solve them parallelly. And all of this was made available using the D-Wave Leap cloud computing service. So the fun part, results. So what you're looking at here is a result matrix. Each number in these tables is an average of 10 measurements, which is then normalized by the number of nodes in the smaller graph so that we can compare them. The numbers range between 0 and 2.02. 0 meaning that they're completely similar. You can see that along the diagonal, and 2.02 meaning that they're completely dissimilar. The penalties have a fixed value of 2.0, which was decided by trial and error. And this means that every incorrect node mapping from one AST to the other is penalized with an increase in energy by 2 points. The minimum energy is normalized by the number of nodes in the smaller AST of the two code fragments, indicates how many incorrect mappings were made for every node in the smaller AST to the larger AST on average. So from our analysis, we find that the second DQM formulation with the node type constraints is better and more effective in detecting code clones. The second observation that you could make from this table is that there are few false negatives too. Specifically, we expected the energy values in the diagonals to be 0, but as you can see in some cases it's as high as 0.02 or 0.15, and that means that the solution space is being stuck in local minima. But then we implemented the DQM with node type constraints, and we found that everything along all the comparisons along the diagonal were 0.0, which means that the solution space no longer sticks in the local minima and does go to the global minima. And this is because we were able to direct the solution space to the global minima by using the right type of constraints, which are the node type constraints. So the pairs of programs that are very different end up having very high energies, as you can see in the white spots there. And the pairs of programs that are very similar, when you compare along the diagonal, when you compare a program with itself, you end up having very low energies, which means that which validates our hypothesis that the lesser the energy, the more similar the code fragments are, the higher the energy, the more dissimilar the code fragments are. Which begs the question, how are we able to detect type 3 clones? So upon observation, we found out that at the energy threshold of 0.9, we realized that the codes start becoming very dissimilar. So just below 0.9, we saw that it is able to detect type 3 clones because we already knew the ground truth. So to give you an example, we had two pieces of code. Everything about them was similar, except for the fact that the first one on top has a for loop, and the same functionality was implemented in the second one with a while loop. And the resultant energy of comparing these two was 0.88, which means that it was right there in the optimal range to say, okay, this is a type 3 code clone. And here you can see the time performance and scalability, because that's a question that we ask a lot in quantum research. Is there a quantum advantage? So you can see along the diagonal that the energies are much higher, that the times are much higher, and we found out that it takes much longer to compare ASTs that are similar than they are dissimilar. And to give you a statistic of what we actually found was this. So The smallest code fragment compared with itself had 14 nodes. So that means it has 14 times 14 variables, which is 196 variables in the solution space. The largest piece of code fragment, had 68 nodes in its AST, which means it had around 68 times 68, which is 4,624 variables. So there's a 2,259% increase in the number of variables in the solution space from 14 nodes ASTs compared with themselves to 68 node ASTs compared with themselves. And even then, the 14 node AST took 109 milliseconds to solve, and the largest one took 190 milliseconds to solve, which means that there's only a 75% increase in the amount of time it takes to solve the smallest solution space to the amount of time it takes to solve the largest solution space. This is encouraging because now we're able to see that even for small programs, quantum annealing is a scalable way to detect code clones. Of course, we are limited by the number of qubits we have, and therefore there would need rigorous assessment and benchmarking with bigger pieces of code when there are more qubits available. But it is very encouraging to know that it is possible to get quantum advantage from this. So, conclusion and future work. The key takeaways would be that software engineering problems can be expressed in the form of a QUBO or a QDO by including novel constraints into it, and it can be tailored to different kinds of problems. There are many optimization problems that can already be solved on quantum computers and quantum annealers. It's just a matter of getting creative with the kinds of problems you solve and how you express them to be able to use quantum computers to solve them. And lastly, even though quantum computers cannot be used standalone for commercial large-scale purposes, there are lots of avenues and research gaps where we can find out how to use them in a otherwise classical workflow to get a hybrid workflow and use them even today for applications in science, programming languages, and software engineering. Lastly, I'd like to thank my advisor, Professor Cristina Lopes, for supporting me throughout this research, and also the faculty at USC, who granted me access to their Advantage Quantum Annealer, where I could learn and play around with lots of algorithms to get a feel of how to actually use them. Thank you.
Thank you. Very exciting work. We have time for questions.
Yeah, thank you, especially for the introduction to quantum computing. I was wondering about debugging and how did you come to this QUBO configuration? So, like, were you sure that you configured the service right to measure the actual table that you showed us? So, like, how did you find out when you made a mistake?
Right. So essentially you're asking is, how do I know that the algorithm is correct, even though that quantum annealers are probabilistic and not deterministic, right? Thankfully, like I said, it's an implementation of simulated annealing, right? So there is a simulated annealer available in the D-Wave library that you can use to verify your programs at a smaller scale. And when you implement those algorithms on a quantum annealer, you are given a resultant energy back. But every time you give the quantum annealer a problem to solve, it is repeated 100 times or 1,000 times, depending on what you want to achieve from it. And that is how we make sure that the majority of the solutions are at a certain energy level. So that means that, for example, 60 out of the 100 shots that it takes to solve the same problem on it are pointing towards a certain configuration of the variables. It means that by a majority voting preprocessing algorithm, that this could be the most feasible solution. So that's the thing about quantum. It is not deterministic, it is probabilistic, but you can increase the probability of going to a certain solution by setting the right constraints. So that's exactly what we did. We increased the probability by adding the node type constraints to make it go to a global minima.
So if I can just add to his question, the other thing that gave us a guideline was that we had the ground truth, right? So we knew which ones were clones, which ones were sort of clones, which ones were not clones. In fact, throughout this experiment, there were many times that we had bugs, and we were getting indeed the wrong values, and we were like, why is this like these are absolute clones? Why are we getting an energy greater than 0, right? For Samyak,
yeah,
it took us a very long time to be okay, and then trial and error, we were able to adjust the panel.
Exactly.
Thanks for great talk. I have a questions. So when applying the quantum modeling to the clone detection problem, does it give any provable advantage over classical computing? I mean, it's basically a graph isomorphism problem, right?
Right.
And there's of course there's no polynomial time classical algorithms that give that solve the problem, but still there's so many heuristics and engineering techniques that we can solve the problem by classical computing. So I guess if there's any quantum modeling specific advantages over classical computing?
That's actually a good question. There are lots of classical graph isomorphism implementations that are efficient. But the objective of this paper was to show that quantum annealers, quantum computers can be used for solving these problems. And I cannot really say for scale, but for the problems that we had and we knew the ground truth for, it was able to scale pretty well. As you can see that there is very less increase in the time it takes to solve a problem as compared to the increase in the size of the problem. So quantum advantage can be classified into multiple categories. It could be quantum advantage in terms of energy usage or time or theoretical complexity of the algorithm itself.
Then have you checked the real physical runtime between them, the classical version and the quantum version? Have you compared?
No, it is still an area of further research. The reason we were not able to completely put it in two buckets is that, okay, this is definitely quantum time, this is definitely classical time, is because we used a hybrid system. So in the hybrid system, to be able to solve larger problems, we traded it with complete dissection of the times, because in the hybrid system, it's used to solve everything on quantum processor, CPU, and GPU.
Oh, but we can compare the hybrid version and the classic version.
Yes.
So, but still there's no comparison, right?
There could be a comparison, but it is difficult to pinpoint which part is the quantum advantage, purely quantum, because it's using CPU, GPU. But yeah, there is a way to compare.
Okay, thank
with
you.
Purely classical.
Thank you.
Okay, that is all the time we have for questions. Let's thank the speaker again.